Good morning, everyone, and welcome to the IBM Qiskit Quantum Seminar dedicated to you, the research and academic quantum communities. I am your host, Zlatko Miniv from IBM Quantum Research, and today I'll have the pleasure to welcome here Cristina Cirstoiu in just a minute, who will tell us about some very interesting research. Now, before we get there, I'm so glad you joined us on time. We have a tradition to give everyone just a minute or two to tune into the live stream and to fire up those fingers and to reply to our favorite question, which I see some of you already getting a start on, which is, where are you guys tuning in from today? Now, you can reply to that in the comment chat box located somewhere on your screen, above, below, left, or right. And that's the same place where you can ask questions live of Cristina, myself, and even interact with each other. We usually get a lot of that as well. So we like to keep this a very lively and interactive discussion. The seminar will stay recorded, but we can only have this live chats Fridays at noon Eastern Time. So to know what's coming up, click like and subscribe. So today, folks, it's my pleasure to kick it off quickly and early for episode number 162 with Cristina Cirstoiu, who's a senior research scientist at Quantinuum. Hello, Cristina. It's a pleasure to have you.
Hi, Zlatko. Thank you. It's a pleasure to be here at the Qiskit seminars.
And where are you dialing in from today yourself?
Today I'm dialing in from Amsterdam, but I'm usually based in Cambridge.
All right, lovely. So allow me to introduce you to our audience. Cristina, before joining her current position, was a researcher in computer science at Oxford University until around 2019. Cristina obtained a PhD in physics from Imperial College London on quantum information theory and a master's in mathematics from Cambridge University. So with that, Cristina, take it away.
Thank you very much. So yes, like Zlatko said, my work is mostly focused on theoretical aspects of quantum computing and software. So this is going to be largely a theoretical talk. But because Quantinuum is focused on building ion trap-based quantum computing, I get the nice perk of having a beautiful picture in the background of some of the experimental setups that my colleagues are building up in the US. So in this talk, we'll take a computational view of how classicality emerges from decoherence and noise mechanisms. And we're going to see some constructive frameworks and blueprints, if you want, of how one can come up with classical simulation algorithms for noisy quantum tasks. So one of the main motivations for building quantum computers is that for certain applications, there is a separation between the running timescales of algorithms that solve that problem in the classical versus quantum setting. So you have examples where you have an exponential separation, like for problems like factoring, and many other applications in simulating quantum dynamics and even sort of learning quantum states. So this is a sort of cartoon that I'm sure many of you have seen before. And this picture usually works in the situation when the quantum algorithm or quantum circuits that built up that algorithm incur no physical errors. But sort of quantum computers today are physical implementation of very small physical systems. So they're subject to errors, and you have here some sort of the diagram of where various types of quantum computers are placed in terms of the average 2-qubit error rates. So those correspond to the primitive operations that you have in your quantum algorithm. And so typically these range from 10 to the minus 2 to 10 to the minus 3 for various platforms. And ideally, one is interested in sort of what is the potential of this near-term regime where you have enough number of qubits that your system or your application cannot be easily simulated classically, but still the errors are low enough that the overall errors in your application is small enough. Now, in this picture, and usually people talk about finite level of error for the primitive operations, for the 2-qubit operations. But overall, errors in a quantum computation will scale with the application size unless additional mechanisms are put in place, such as trying to mitigate for errors, or later on applying the substantial overheads to correct for those errors. So if none of these kind of noise suppression mechanisms are in place, then the scaling of how the total runtime of an algorithm goes with the application size will be something more like the blue curve here. So one usually hopes that for error rates per gate that are small enough, then for particular applications, one might find themselves into this nice region where the scaling crosses below the complexity of a classical algorithm for a while before noise kills off that coherence, and then you come back into a regime where classical algorithms can still compete because you're incurring a very large error overall in your computation. So if you want to think at the very extreme situation where the error rates are very high and the computation completely decoherence to a maximally mixed state, then the algorithm in that case, the classical algorithm that you're looking at, is just random guessing. So if your computation is completely decohered, then it would be just as if you're running a random guessing classical algorithm. Okay, so for the rest of the talk, we're going to try to kind of address from a computational view, from a kind of quantitative perspective, what happens in this regime here. So where your computation is noisy, and you're looking at scaling in application sizes in this sort of regime, and trying to come up with classical algorithms that can match this kind of scaling over here. So we're looking at when this kind of noisy computation crosses over back into a classical regime. So the kind of main question to have in mind is that of when quantum computations become easier to simulate classically, where you're in the presence of a finite level of errors. And here we're talking about finite level of errors per primitive operation, per 2-qubit gate. So let's have a look first at what does an efficient classical simulation mean. What do we mean by that? So we start off, quantum computation, regardless of the algorithm, typically involves preparing some initial state on an n-qubit system, applying a sequence of operations, single and 2-qubit gates, forming a big unitary that acts on a 2 to the n dimensional vector space, and then measurement in, say, the computational basis. Now, the Born rule tells us that the outcome of some classical bit string occurs with probability equal to the sort of square overlap between the computational basis state and the computation prepared on by the circuit. Now, trying to come up with an efficient classical simulation for the Born rule is one of the strongest form of simulability that one can place. But there are also weaker forms, and that depends on asking for a classical algorithm to do a particular quantum task. So that's what we will mean by classical simulation in this talk, and what that quantum task is, it will depend on the particular setting and the particular application. And efficient, in this case, we're looking at the asymptotics. Like I said, we're looking at polynomial scaling in the number of qubits. Now, there generally are like two quantum computing tasks that people care about, and they're kind of form the basis of many of the quantum algorithms. So one of them is sampling, and that is to produce a sample from this output distribution of a set of target states. This is an interesting sort of task because it comes with asymptotic hardness guarantees, and it has formed the basis for many experimental proposals and demonstrations of quantum advantage. The second type of task that one could be interested in is that of computing mean values, so expectation values of some observable with respect to some state that we've prepared on an n-qubit system, for example. Now, generally, this type of computation, so estimating this type of computation up to an additive error when the unitary U consists of a polynomially sized circuit, is generally a difficult task. However, there are classes of unitaries for which this type of estimation can be made efficient. So one such example of an efficient subtheory is that of what are called Clifford unitaries. And here's, in this slide, we're going to quickly review some of the background that's needed for understanding this. So the Clifford unitaries end up being those operations that permute the Pauli operators. So we can form a complete and orthonormal basis by constructing tensor products of single qubit Pauli operators, identity X, Y, and Z. And we can view this as a 2n-bit encoding. So we can have a one-to-one map between the set of Pauli operators and 2n bit strings. Because of this type of encoding, and because of the fact that we've defined the class of Clifford unitaries as permutations of Pauli operators, then one can easily see that in fact computing expectation values, these type of expectation values, can be efficiently done in order n squared. Now, another interesting aspect of Clifford operations is that they are generated from a relatively small set of gates consisting of control knot, Hadamard, and phase. So this forms a class that's efficient to simulate classically. And in order to achieve a universal quantum computation, we need to add one more ingredient. For example, it is sufficient to add a T-gate to enable that universality. In this case, we're going to look at a larger class of continuous rotations around Z, that together with the Clifford operation also form a universal set. Now, what about this universality enabling gate? So we can write down a Z theta rotation as a linear combination of the Pauli identity and Z with some factors that depend on trigonometric functions of theta. If we were to, so with that in mind, any state vector that is formed of a big circuit containing Cliffords and a single Z theta operation can also be written down as a linear combination consisting of states prepared with Clifford circuits and these kind of coefficients. And if we had in our circuit multiple occurrences of z theta rotations, then we can sort of bootstrap ourselves, and we see that for every additional z theta rotation, then the number of terms in this expansion will double. So therefore, we end up with an expansion over a linear combination of 2 to the number of non-Clifford z rotation terms. Okay, so we've seen that you can do this at the level of pure states. Now, you can think of doing this similar type of frame decomposition at the level of a unitary channel. And the reason we do that is because we're interested in what happens with computations in the presence of noise. So for that reason, thinking about the computation as not in a mixed state formalism becomes very convenient. So we can have a similar type of decompositions of the now unitary channel corresponding to rotations around Z, and it will have this decomposition in terms of identity, Z, and S unitary channels, with the coefficients appearing in front of that being quasi-probabilities that are also going to be trigonometric functions of theta. So just as we have had before in the mixed state formalism, so when we're talking about now unital quantum channels, these also can be expanded as a linear combination of now Clifford maps. And even though each term can be efficiently computed, in general, the number of such terms is going to be an exponential set. So what happens when we, rather than having, when we have a polynomially sized number of terms in this decomposition, when the computation can be approximated by by these terms, then that means that in that situation we can talk about constructing a simulation of that computation that's going to be efficient, because we have a polynomial number of terms, and each of the terms can be efficiently computed in a polynomial number of steps. So I've given you kind of an example of what happens in the case of Clifford operations, but there are other what are called like efficient free subtheories, essentially classes of circuits that are classical in the sense that they can be simulated efficiently, and in order to achieve universality, you need to add one extra ingredient. So you have like here a series of examples of papers that address this kind of aspect. And we find such classes like match gates and Gaussians in addition to Clifford operations. So this is kind of like the rough picture that one could have in mind, although it's a little bit of a cartoon.
Before I let you get there, Cristina, a couple of maybe quick questions on the part so far. I think it's very interesting, especially the Clifford plus RZ and the two decompositions of it. For one, everything you end up running, I think, on most, if not almost any quantum computer ends up being something like that. Especially when you transpile a device, when you take a circuit and you compile it or transpile it down to the native gates on many of these platforms, you end up with Clifford gates like CZ, CX, which are two qubit gates, and then your usually all the single qubits that are calibrated are square root of x's or x's, and there's an RZ gate. And usually you end up with just the RZ gate. So almost any of the computations we end up running ultimately have this structure, which I think is very interesting. Although the number of non-Clifford gates you end up with will depend on whether you're using like a CZ or a CX in the basis, so that 2 to the n kind of depends on the way that you've decided to transpile your circuit. So maybe this is kind of a question around if you can tell us a little bit more of this connection, and it seems like this might even give you some measure of the complexity of the circuit that you want to run, is how many of these non-Clifford gates you have. But maybe you can tell us a little bit more about that.
So so there's got to be, okay, let me see if I kind of completely understand your question. So one part of that was about looking at different type of basis sort of decompositions. So like C0 plus Z rotations, or some other type of some other universal class, right? Of Clifford. Is that what was the question?
Right. It's maybe there's two pieces to it, and it's a little bit broad in scope if you want. But for a given quantum circuit, I can choose a kind of a different Clifford plus Z structure. There are many ways to map it to Clifford plus Z. There isn't just one version of that. There are many different ways.
Yes.
So while there is this exponential scaling of 2 to the n, it seems like you also have a lot of optimization freedom there as well.
For sure.
Which I wonder kind of what, whether there's something to gain from that.
Okay. Yeah. Okay. Gotcha. So like this, in terms of the scaling, regardless of what decomposition you have, is you're gonna incur the same scaling, because if you have one type of decomposition to the other, then that's gonna have constant overhead in terms of mapping from one to the other. That's talking about asymptotics, though. So what I gather you're more interested in is having gains at the level of when we're talking about finite sizes, finite number. What's the kind of maximal number of non-Clifford operations that I can run before there's a bottleneck in the classical computer? And so Sergey Bravi and co-authors, they've done a lot of like interesting work around this, and trying to from his your colleague from IBM. So they've done a lot of interesting work on simulating. I think that some of the numbers may be a bit out of date. Around 50 number of T gates, 50, 60 number of T gates can be done classically, but after that, if you kind of if you keep on adding, then you're gonna hit a wall in terms of compute time on a classical system. So even though we're talking about a logarithmic number of non-classical, non-Clifford operations, then when it comes to running things practically on finite size system, there's still going to be a bottleneck. I think, does that address the question? Or
I think maybe that's good for now for that.
Okay.
And the second, can you give us a little bit? So you showed us two Clifford plus Z decompositions, the pure state and the mixed state. Can you kind of motivate again for us? What does this latter one give you, or what are the advantages, disadvantages of looking at it with either the first or the second? Why use the second if the first is sufficient? Tell us a little more about that.
Okay, so the second decomposition, we're thinking about it, doing it at the level of mixed state, because ultimately we want to construct a classical algorithm in a noisy that kind of matches the behavior of a noisy computation, and that's going to happen in a mixed state formalism. You're not going to have a pure state that's going to, your system is going to interact with an environment, so that's going to be best described in a mixed state formalism. So that's why going into that, what happens to at the level of mixed state is going to be beneficial in order to see almost like a comparison between what happens with a noisy computation and what would happen with a classical simulation that's aiming to reproduce that computation.
And is the somehow this is not particularly well formulated because they're obviously totally different simulations of a mixed versus a pure state. But maybe if I try to do a pure state with the mixed state formalism, is the cost similar or much bigger? And I ask that because in one case you have just two coefficients, but they're complex, if you want. In the other case, you have three coefficients, but they can, they're quasi-probabilities. They can be negative. So usually there's some sampling overhead because of the negative signs you end up with there.
Right, and that's what gives you, the power of using universal quantum computations, right? Because if you had probabilities, then it would have been easier to do with sort of Monte Carlo sampling type of approaches, but yeah. So in general, if you're thinking about if you can map a sort of a mixed state, right, to a quantum channel to a state that acts on now a much larger Hilbert space. So this is what's called, like, for example, Stein-Spring dilation theorem. So through this sort of perspective, you can think about simulating sort of mixed open system type of computation using this doubling approach of the doubling of the Hilbert space. So that's one way of thinking about it, and why it's you get this kind of different type of decomposition.
Great, thank you very much. Let you proceed.
Yeah, thanks. Okay, so to kind of wrap up that part of the discussion, then in the noiseless setting, we have this kind of cartoon where we have a classical theory, and then maybe a little bit of non-classical type of operations, and now we have various blobs, various kind of subsets that correspond to different approaches to classical simulation based on Clifford's, based on low entanglement states that can be represented with matrix product states using tensor networks or through matchgate. And the kind of computation that you're targeting, usually you want to be kind of as far away as possible from all of these subsets that are close to a classical subtheory. And the kind of intuitive idea is that once you start adding noise, then to your computation, then noise could potentially bring you closer to one of these sets that are classically simulable in when we're talking about the asymptotics. So in effect, we're looking at when does a noisy process in itself kind of induces a truncation in terms of the expansion of your computation. So when the number of terms that appear that are most significant in that computation are polynomial in size. And so there have been a series of works that kind of try to make this approach concrete and sort of by building for different classes of algorithm, building these type of efficient truncations in order to produce classical algorithms that scale polynomially in the number of qubits, and sort of to approximate the output of a noisy computation. So these kind of ideas have been applied initially in the context of random circuit sampling task, first by Gao and Duan, and then later on by Harmonic, Gao, Landau, Leon Vazirani, who kind of brought down the complexity of to what you see here, basically a polynomial in the number of qubits, and sort of an inverse with the approximation error of that task. But you incur an inverse scaling with p, when p in this case is going to be the physical error rate in that computation. And then there's kind of other similar ideas for other tasks like boson sampling, and sort of constructing simulations using tensor network approaches over here that are driven by this similar ideas of truncating, ways of truncating that are kind of given by how the noise behaves. So for the next while, I'm going to be sort of focusing on one of the works that we've done last year, which is to come up with such an algorithm to construct such a classical algorithm for the task of computing expectation values for noisy parameterized quantum circuits. And after that, I'm going to show you how those ideas can also give us a kind of different, maybe a different perspective on the construction for noisy random circuit sampling, and then it's give us a whole blueprint of how to construct this type of classical algorithms that are polynomially scaling and approximate noisy quantum tasks. Okay, so we're going to start off by looking at parameterized quantum circuits, and these appear in a variety of NISQ applications, such as variational quantum algorithms like the quantum eigensolver, dynamical simulations, data loading for quantum machine learning. So they've been quite used a lot in the last few years. So the task in these kind of in many of these applications is that you are given a unitary that is parameterized by a set of angles. Here we call them by theta 1 up to theta m. And we assume that these have been synthesized into a Clifford plus Z rotation type of decomposition just for convenience and to link back with the introductory part. And the task is to estimate the expectation value of some Pauli observable with respect to this parameterized circuit. Now we're going to consider the noisy version of this task, where each of the rotation angles is followed by a Pauli noise. You can think about this as a decoherent process that, with some probability p, an error corresponding to an x, y, or a z single qubit operation has appeared. Or if you want more simply, you can think about this as a single qubit depolarizing channel, and a similar story emerges there. So in effect, if you look at the kind of type of expectation value that we want to estimate, this is going to be a function that depends on these parameters, theta 1 up to theta m. So we can think about this in a Fourier basis. So we can take the Fourier transform with respect to these independent parameters. And what that might look like if we only had two parameters, something like you have here in these figures. Now, in this Fourier basis, the kind of effect of noise is going to be to contract these Fourier coefficients. And in the right picture here, you see the output of a noisy computation, not with this simplified error model, but this is actually on an actual hardware. If we were just talking about a depolarizing channel, then we wouldn't have these additional modes appearing. So there will only be kind of a contraction over these coefficients here, with possibly different weighting in the contractions. So Okay, so the goal that we want to set ourselves is to construct an algorithm that produces an approximation of this noisy expectation value.
And Cristina, can you remind us what is lambda 1 and lambda 2?
Oh, of course. So here it's just maybe like you can think about lambda 1 and lambda 2 as being the Fourier sort of, if you take the Fourier transform with of a function, so these would be like the Fourier modes corresponding to that. So for example, z of theta, cos theta is going to have a Fourier Fourier coefficients corresponding to plus minus 1.
I see. Yeah, so theta is between 0 and 2 pi, and so you have this discreteness.
Yeah, I mean the details of this are not sort of super important. It's just to illustrate the idea that if you think about this in this kind of Fourier basis, then it becomes a little bit easier to see what the effect of noise is. It becomes a contraction of these Fourier coefficients.
Is that somehow similar equivalent to saying that you look at you look at this? So this is in theta, Fourier in theta, because I'm thinking of the noise is, this kind of noise is diagonal in the Pauli transfer matrix basis, which is a bit like a Fourier transform itself. There's a Walsh-Hadamard between the bit strings and the Pauli basis.
Yes.
I'm trying to see if this is related or different.
So it's a little bit different in that it's not a it's a little bit different in the sense that it's not a Fourier transform over the bit strings. It's a Fourier transform. So the Walsh-Hadamard function transform is when you're considering where it's a Fourier transform over, not over U1, it's over Z2. You have it's over bit strings, right? So in this case, it's a little bit different. You're considering your function as as being dependent on these continuous parameters and just taking a Fourier transform with respect to those continuous parameters. It's a little bit, it's not, so if you, so there are some differences when you consider, what you're like, Fourier transform all of the outcome, respect to the kind of outcome bit strings.
Okay.
But in some sense, their behavior will sort of be the same. So like in this case, we're looking at the expectation value. So we're not sampling. We're not kind of picking a bit string.
Okay, thank you.
Okay, thanks. Okay, okay. So let me jump into kind of what's the kind of main result of this work is that this low weight simulation algorithm, as we call it, and this has been work done with Enrico Fontana, Manuel Rudolph, Ross Duncan, and Ivan Runger. And in this work, we showed that you can construct an approximation G tilde of this noisy cost function in a way that if you look at this average simulation error, and the measure that you're using here is an average, an integral over all independent parameters. So it's a 2 norm over this set, and that decays exponentially in the physical error rate. So the probability of getting up, of having an error in one of the single qubit gates, and the runtime is going to be polynomial in the number of qubits, and is going to scale as n squared m2 to the L, where L here is just is going to be a cutoff parameter that we'll see that we have some control over. So the kind of main take-home message here is that independently parameterized noisy circuits are going to be, on average, efficiently simulable. So I'm going to kind of go through how we can construct this algorithm. And now we're going to see that because we're computing expectation values, it's going to be more convenient to work in a Heisenberg picture where we evolve the observables rather than evolving the state. So this is an equivalent picture, but that means that now we apply basically the circuit onto the observable that we want to compute. And the convenience comes from the fact that this Heisenberg picture plays very nicely with an incoherent error model like a Pauli channel, because in that case it just acts the noise channel just acts as a fixed point up to some coefficient that will depend on the physical error rate. And as Latko mentioned earlier, there is indeed a way of getting these coefficients here in terms of the Pauli error rates by using also the Walsh-Hadamard transform. Okay, so with that in mind, let's go back to kind of the noiseless setting and see how the expectation value will kind of a Pauli operator will propagate through the circuit in this Heisenberg picture. So for the moment, we're not applying an error model because we want to see how the complexity kind of scales and how information spreads. So we start off with computing the expectation value of the Pauli, and we propagate through the first layer of Clifford operations. Now that update, we've seen that takes order n squared time. Then we're going to hit a single qubit independent Z rotations, in which case we're going to have a series of choices. If the Pauli corresponding to that particular single qubit is going to commute with Z, then there's only one way, and that way is going to be that the Pauli is going to remain the same. So there's nothing to apply here. So we label that with a W that we call 0. So that's going to be what we call the weight. Now, if that Pauli on that single qubit is going to be X or Y, then that's going to be mapped to a linear combination of X and Y with coefficients that correspond to these trigonometric polynomials. So at this point, if the Pauli is an X or a Y, then we have two branching choices. We can either go one up, so we call that W1, or down, W minus 1. And then the new updated Pauli is going to be either P or P times the applying the Z on that particular qubit. And now we kind of keep on going and pushing the Pauli operator through the circuit. And every time it hits this non-Clifford Z rotation, we may have a choice of splitting into a linear combination. And this expectation value is going to be a big sum over all the possible contributions over all of these different branches in this diagram. Okay, so now what happens with noise is that every single branch in this kind of split is going to incur some dampening coefficient that's given by by this kind of channel eigenvalues corresponding to the error model that we applied to that. So this is maybe a little bit too much for this kind of I'm quite behind in what I wanted to say, but just to illustrate the idea is that if you add in noise, then you can have a similar decomposition into, now we're doing it at the level of mixed mixed computation. We're doing it in a Pauli transform matrix representation, and we can also split up the computation in terms of 3 terms, and each of which is going to depend on the physical error rates. So we have this kind of sort of big expansion into where you get a set of coefficients depending on the angle, and then with those coefficients, there's going to be an associated expectation value that, in this case, is going to be efficient to compute because it's going to consist up to these coefficients that depend only on the error model is going to consist only on the Clifford operation. Now, this is going to be the expansion of the noisy expectation value. And what we're going to do, we're going to say, if I only include those coefficients that correspond to a fixed number of splits in this truncation path, then that means that corresponding path is going to be damped by a coefficient that's going to be exponential with this kind of number of the sum over all the lambdas. So the number of times you split, you're going to incur an additional dampening factor given by qx or qy. So in terms of the path decomposition, you end up with a constraint where the only paths that you consider are the ones that have split up to L times. And the number of such non-zero paths is going to be at most 2 to the L. And as we've seen previously, each of the evaluations of each of this path, it is going to take a polynomial number of steps in the number of qubits. And here M, recall that M is the number of non-Clifford operations, and that can also be kind of scale polynomially with N. Okay, so now we've seen that we can construct a function that that is efficient to calculate, and the only thing that's remaining to do is to show that this is a good approximation of the noisy expectation value. So how do we do that? We observe that the trigonometric functions in this expansion are given by trigonometric functions, and they're going to be orthogonal in this because we are saying that the parameters are independent parameters. So we can look at the average error over all independent parameters, and we can bound that by this factor q to the power of 2L plus 1, where we recall that L is the truncation factor that we have. Now, this other term here is just going to be bounded by the norm of the observable that you want to compute, so it's going to be a constant, and that leads you to a bound on the approximation error of this reconstructed classical surrogate, if you want, that's going to decay exponentially with the error rate and this cutoff parameter. Okay, but so I've sort of very slowly gone through a simplified example. The idea, the kind of main take-home message is that you can put a series of generalizations on what I have said, and you can construct with more general Pauli noise. You can look at probabilistic versions where you fix some of the non-Clifford rotations. But the kind of overall story is that decreasing noise is going to be more important than increasing system size if we're thinking about this type of asymptotics. So in other words, Louisa kind of gives you a classical surrogate of the expectation value of a parameterized quantum circuit, and you can compute that with runtime that scales polynomially in the number of qubits, and but it also scales exponentially in the inverse of the error rate. So that is sort of to be expected, right? If you have a higher error rate, then it's going to be easier to simulate classically. And similar kind of ideas have emerged in a series of other papers approaching this problem from different perspectives. Now, I was talking about asymptotics, and what about finite size heuristics? You can use this kind of similar construction, the construction of the algorithm that are presented, to build up a surrogate of a noisy landscape. And this is going to be most useful for computing mean values of circuits at multiple parameter values. So some of my colleagues, some of my co-authors went on and tried to see how this algorithm can do in a finite size settings. And they've applied it to one of the kind of biggest quantum computations that have been sort of done with a quantum computer recently, and that's this paper over here that looks at expectation values of observables in a sort of dynamical simulation of an Ising Hamiltonian. And in this case, the IBM team looked at error mitigated observables. And so they're really pushing the kind of boundary from, if you remember at the beginning of the talk, we have this kind of physical line that's going into classical simulability, and error mitigation can help sort of make that, bring that a little bit down, so that you're not, you're kind of reducing some of the effects of the noise. And in this case, the kind of Louisa can give a good approximation of what happens in that error mitigated quantum computation. And there are other types of truncation that can lead to kind of similar results. Okay, and because I only have a few minutes, and I've made the mistake that no one should ever make, which is to only go through half of your talk, I'm gonna say that similar ideas can be applied to the random circuit sampling task, and we have the sort of recent results by Aharonov et al. That perform kind of truncations in if you like, in the Fourier basis that are motivated by the effects of noise on the different paths that you can take in this kind of big computation that you look at making like a big linear combination of. Now, using the ideas from Louisa, we can also basically have a slightly different approach, but ultimately it leads to the same point of building a classical algorithm that's polynomial in time and scaling exponentially with the inverse error rate for the task of approximating random circuit sampling. So we'll have a kind of similar now split of the different paths that one can take. Only in this case, we are looking at 2-qubit unitary operations. So we're gonna end up with, rather than a 2 split that we have when applied single qubit Z rotation, we're gonna have 15 different choices. And the coefficients, there are things that you can relate to some nice group theoretic aspects, which end up being something like you can construct essentially like a lookup table. And in a similar fashion, like I've described for Louisa, you can propagate those Paulis through the circuit and put a truncation rule on how many of those different paths you keep in your computation. In this case, this is going to sort of give you, like if you start with a Pauli, you kind of end up with a Pauli, but you also only compute the expectation value of that Pauli. Here you're interested in output probabilities, but you can still expand that out in terms of Pauli operators. There are like a few other additional tricks that one needs to do in order to kind of get the complexity to a level where you get a similar kind of scaling that's polynomial in n, and sort of exponential only in the truncation parameters. So in the end, you end up with a construction that gives you an approximation error that also kind of decays exponentially in this cutoff parameter and the error rate. Once you kind of make some certain assumptions on the fact that kind of random circuit sampling have this anti-concentration property. So long story short, if you apply similar ideas that I've explained for the Louisa type of algorithm, you end up with constructions that are very similar to what you get from this paper here, and a similar results. Although some of the prefactors can be a little bit improved. Okay, so this can be even further generalized into an algebraic framework, but that would kind of involve all of the different ingredients that were put into this construction of these algorithms. So the type of structure that you have on your circuits, the approximation bounds that now are going to come from various generalizations of Parseval's theorem, and you can, with certain kind of classes of random circuit, certain classes of circuits, you can derive very similar results. So now I'm gonna do the other thing that you're not supposed to do in a talk, and jumps right up to the end of it, and wrap up and tell you that, okay, in this talk we've looked at a framework that tells us how to construct classical simulations for noisy computations, and with a kind of big remark that we're talking about asymptotics. We're talking about what happens in the kind of right corner of the image that we saw at the beginning. What happens when you add noise with the sort of separation between classical and quantum. And so there are kind of many questions whether how practical these kind of aspects are. And although we've seen that a version of Louisa can be applied in a finite size kind of problem, that's obviously bound to kind of fail at some point, because as you sort of reduce the error rate and increase the size of the computation. With that, I'm going to kind of acknowledge my sort of co-authors, and these are the kind of various bits and pieces of papers that I've been talking about throughout this past hour. Right. Thank you very much.
All right. Thank you very much, Cristina. And maybe the first question is a very hard question, which is the backpropagation part. Which paper is that in?
That is a very hard question. I mean, I don't know of where you would go for the first kind of, for the first where that first appeared, but I can tell you can find a little bit about how to propagate Pauli backwards in the Heisenberg picture through a circuit if you look at the first paper here. But it's, I think if you look at Gottesman notes, the Gottesman book, then you will definitely find that those similar ideas. It's like from 2000s at, if not much earlier.
Great. Okay. Thank you. And folks, this is a great time to post your final questions as we come up on the end here. There was a question from earlier when you showed that kind of cartoonish graph of all the different simulation methods like MPS, Clifford, and so on. How seriously should we take that picture in terms of the overlaps? For instance, can MPS represent some or all Cliffords to some degree, or is that more of a?
Oh yeah, it's a cartoon. It shouldn't be, the overlaps are, I couldn't have done it in a way that is visually appealing. So yeah, you're right. So if there will definitely be overlaps between MPS match gates and Clifford operations. There's also match gates are a continuous set. The Cliffords are a discrete set. So there are a lot of differences between different classical simulation methods. That's why typically, it's kind of difficult to see which one is going to perform the best for a given circuit in a, if you're looking at simulations in a finite size regime. Unless it's something very clear, like, oh, this is a very local circuit that has very low entanglement, so MPS methods are going to do very well, or if it's only a Clifford. So in those regimes, okay, we can say something, but if it's somewhere not as clear and somewhere in between, then I think it's generally quite difficult, and I don't know how to make that cartoon in a way that's very rigorously captures the complexity of all of these different sets of kind of classical subtheories.
Thank you. And now that we've learned a lot more about what simulation methods can do, especially in noisy systems, what does this tell, say, experimentalists and folks who wants to look at what problems to think about or work on near-term devices? Can you give us some perspective?
I think there are a lot of results, like apart from these ones, there are a lot of results on kind of limitations of noisy quantum computations. And so there is a point where if you just leave the computation noisy, it's not going to scale. And you can try to add additional things like error mitigation, for example, and that's not something that the framework that I've talked about includes immediately. There are other results that say, in the worst case, error mitigation will not lead to it's not going to be scalable, but that also leaves room for the average case situations where you could find that your computation is noisy. You add some error mitigation method. Maybe you even have some way of verifying that computation, and in that case, you're going to be you could say something that you can do something on a quantum computer that's not classically possible. So it's talking about sort of limitations with respect to scalability mostly. It's not saying that you can do a classical algorithm if, these kind of classical methods to approximate noisy computation, they're not immediately transferable to finite size regimes. You can try, but as a heuristic, but that's going to be a heuristic.
Thank you, Cristina. And maybe final question here from Maple. Is it sufficient to use amplitude damping noise, dephasing noise, and depolarizing noise when we look at simulations, or should we really be using other kinds of noise models?
Well, it sort of depends on your context, and it depends on the system and on the platform. For some platforms, like superconducting devices, you would need to consider the effects of amplitude dampening. Zlatko knows a lot more about that than I do. For ion traps, for example, we have other sources of errors. So other error models are going to be more relevant to what you're going to get out of the computation. Typically, theorists like to use depolarizing noise and maybe Pauli noise because it's easier to manage and prove things with that. But there have been some recent results from example, from the Berlin group, Jens Eis's group, and Ihui Kwek, where they do some interesting expansions on non-unital noise. So you can play around with that in that setting as a theorist, but it can be a bit more difficult sometimes. I don't know if that fully answers the question. It's a very difficult question. I think it's very difficult to model a quantum computer, well, using these, simplified error models for which you can do something theoretically.
Right. Well, Cristina, with that, thank you very much for the great presentation, and folks for dialing in. This talk will stay recorded, so you can watch it and go back through it. But to know what's coming up and to discuss and interact live, click like and subscribe. And see you every Friday at noon Eastern Time.